Welcome to qnawire.
Hi, so over here what we're going to have is the h2p04 minus ion that is going to have a pKa equal to 7.2, and we're asked to prepare a 1 liter buffer with a total concentration of phosphates of 0.05 molar and at a pH equal to 7.5. So the first thing that we need to do is, well, the materials that we're going to be employing are going to be sodium h2po4 minus and sodium hydroxide of a 1 molar concentration. And this is going to be, sorry, here now without the minus, and this is going to be a crystalline solid that we're going to be able to measure in the balance. So the first thing that we need to do is calculate the ratio in between the concentration of HPO4 to minus the conjugate base divided by the concentration of H2PO4. The reason for that is that our Henderson-Hasselbalch equation tells us that pH is going to be equal to pK plus the logarithm of the concentration of the conjugate base divided by the concentration of the weak acid. Sorry, here to minus and over here with a minus. Thus, replacing the values, this is 2.5, this is 7.2, plus the same thing here, the logarithm of these values, what we're going to get is that 10 to the 0.3 is going to be equal to the concentration of HPO4 2 minus divided by the concentration of H2PO4 minus. Now, the next step is going to be considering that the total amount of phosphates needs to be equal to 0.05 mole. What we require is that the initial amount of H2PO4 minus that we're going to get needs to be equal to that same value. It needs to be equal to 0.05 mole. So the reaction that we're going to be taking care of is the following, in which I'm going to write down the ice table in terms of mole instead of molarity. In this case, this is going to be useful because we want to know what is the amount of OH minus that we need to add, because this guy is going to react to produce HPO4 2 minus plus water. My ice table in terms of amount of moles is going to be 0.05. I'm going to add an X amount of the sodium hydroxide, and initially I have 0. Water doesn't matter for our calculations. The amount of change is going to be given by the X amount of OH minus that I added. So we get a equilibrium 0.05 minus X, 0, and X. Remember that whenever we do the ratio of concentrations, for example, HPO4 to minus divided by concentration of H2PO4 minus, this is going to be the same as amount of mole of HPO4 to minus divided by the volume divided by the amount of mole of the acid divided by the volume. So volumes are going to cancel out, and this is the same as dividing the amount of mole that we have of each of the species. In this case, where the volumes are going to be the same and that we have the same solution. So we can replace these values with the ones that we found from our ice table. Of HPO4 to minus, the value is going to be X, and of H2PO4 minus is 0.05 minus X. But previously, from the Henderson-Hasselbalch equation, we found that this needs to be equal to 10 to the 0.3. So we can equate this equation to that. Now we need to solve for x in this equation. So solving for x, what we're going to get is that we're going to pass to the right hand side the multiplication. So x is going to be equal to 10 to the 0.3 times 0.05 minus 10 to the 0.3 times x Putting all of the x's on the same side, we're going to get x plus 10 to the 0.3x. We can factorize the x on this side, so x times 1 plus 10 to the 0.3. And this is going to be equal to 10 to the 0.3 times 0.05. Perfect. So now with this, we can directly get the value for x. That is going to be 10 to the 0.3 times 0.05 divided by 1 plus 10 to the 0.3. The result of x with this is going to be equal to 0.033307 mole. Now, if we recall, x is also going to be equal to the amount of mole of OH minus that we added. And since sodium hydroxide in water is going to dissociate completely in sodium plus OH minus, this is also equal to the amount of mole of sodium hydroxide that we need to add to our solution. Now, using the fact that molarity is equal to amount of mole divided by volume, the volume that we're going to require to add is equal to the amount of mole divided by molarity. Thus, the volume of sodium hydroxide is going to be equal to N divided by the molarity of the sodium hydroxide. This is 0.033307 mole. The molarity was 1 mole per liter. We have a 1 molar solution. So, oh sorry, here I missed a 0. So we get 0.033307 liters. If we convert this quantity into liters, what we get is, you simply need to multiply this by 1000, so 10, 100, 1000. So the volume of sodium hydroxide that we need to add is equal to 33.3 milliliters, or 33.31, if you want to round up to 4 significant figures. Now, we know the volume of sodium hydroxide that we require, so now we want to know what is the mass of sodium h2p04 that we need to prepare our solution. And that mass is going to be related to the amount of mole of h2p04 minus that we require. Let's say that these are going to be proportional to each other, right? So the mass is going to be equal, let's begin with the 0.05 mole of h2p04 minus. Let me take some space. We know that 1 mole of h2p04 minus comes from 1 mole of sodium h2p04 minus p04. After it goes into solution, and we want to take the molar mass of this compound. The molar mass is going to be equal to 119.98 grams per mole, so 119.98 grams in 1 mole of NaH2PO4. So the mass is going to be equal 5.999 grams of sodium H2PO4. If you use a molar mass of 120, the result would be equal to directly 6 grams of NaH2PO4. Because some people like to round them up, and the value would be 120 grams, so directly 6 grams. So these are the quantities that we need to measure, and in order to prepare the solution, the procedure would be the following. Measure 6 grams of NaH2PO4, add some water to dissolve, but not too much water in order for you to be able to add the sodium hydroxide. Then we're going to add 33.31 milliliters of sodium hydroxide 1 molar. And finally, fill up to 1 liter with distilled water. So that would be all. Thank you very much and have a good one.